In today's modern electronic systems, especially those dealing with high power, accurate measurement of current and voltage is essential for control, protection, and efficiency. But as voltage levels increase, so does the need for safe and reliable signal isolation between the high voltage domain and the low voltage control circuitry. And folks, this is where isolation amplifiers play a critical role. They allow precise analog signals to cross isolation barriers while protecting sensitive components and ensuring user safety. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Simon Goodwin from Vishay joins me to chat all about analog output and the isolated current and voltage sensing using isolation amplifiers. Simon and I explore the fundamental principles of current and voltage sensing and the variety of voltage and current sensing solutions offered by Vishay that can get your next design up and running in no time. And before we get started, don't forget to click that link. There you can find even more information about this topic from Vishay. Hi, Simon. Thank you so much for joining me.
Thank you for having me.
Absolutely. So, Simon, we're talking about analog output, isolated current, and voltage sensing using isolation amplifiers today. But before we get started, let's review the fundamental principles of current and voltage sensing.
Yeah, for resistive current sensing, the current to be determined is sent through a low impedance resistor called a shunt. The voltage drop across the shunt is filtered and processed by suitable ICs. When selecting the shunt resistance value, a trade-off must be made between efficiency, the power loss over the shunt, and the amplitude of the measurement signal. Since the output voltage of the shunt is derived from Ohm's law, the output voltage is R times I, and the power loss is P, which is R times I squared in the end. Therefore, the resistance value should be as low as possible while maximizing the output voltage range of the subsequent circuit.
So, Simon, can you give me some examples of resistive current sensing?
Yes, so for resistive current sensing, we can mainly look at two different power ratings or current ratings. One example would be the main battery in an EV, and there we would have very low resistance values to have a low power loss and be able to measure very, very high currents up to, let's say, 2000 amps. And the other extreme would be, for example, power profiling in very low power MCUs, such as, for example, found in the Nordic Power Profiler kit, where we can measure down to the nanoamp range, but need much higher resistance values in between 51 milliohms and 1 kilo ohm. In this picture, you can see the range of shunts we offer for these applications. In the left, you've got the WSBE power shunt, and then we go over from the busbar shunt to SMD shunts, such as the WSLP series or the WSK series, and then to much smaller shunts like used in the Nordic Power Profiler kit for RCL E3 series.
So, Simon, what about voltage sensing? Can we walk through that next?
Yeah, voltage sensing is quite similar to the current sensing, but here we don't use a current, or we don't want to sense the current, we want to sense the voltage in an application. And the voltage is normally much higher than your IC can handle, so we need a voltage divider to divide the high voltage down to a range the IC can handle.
So, Simon, what does Vishay offer in terms of voltage sensing solutions?
Yeah, Vishay offers a broad range of resistors. We can divide them into two main components, the discrete voltage dividers, like normal resistors that are made for voltage sensing, and then chip voltage dividers where we have the whole divider network on one substrate.
So, how can we transfer the voltage signal generated by the shunt or voltage divider over an isolation barrier to yield an isolated current or voltage sensing circuit?
Yeah, to answer this question, we should turn our attention on the ICs that allow to do this. This would be two dedicated chips out of the Vishay portfolio, the VIA series of isolation amplifiers. The isolation amplifier measures a signal on the high voltage side and produces a proportional signal on the low voltage side, which is completely isolated.
So talk to me about the Vishay solution you'd use here.
One example for the isolated voltage sensing would be using the VIA 2000, and Vishay has a portfolio of different devices for different applications. So the one for voltage sensing would be the VIA 2000 SD, and then for current sensing we would have the VIA 250 DD or the VIA 0050 DD.
So could you use the same method for voltage sensing here as well?
Voltage sensing requires a different input. The voltage sensing device is the 2000, which has an input voltage range of 2 volts and is used for voltage sensing, and the VIA 250 DD is used for current sensing with a differential input, and it's produced for much smaller input voltage signals.
So what about isolated current sensing? What Vishay solution would you suggest here?
For the isolated current sensing, we would choose one part out of the VIA 0250 or the VIA 20050. The difference would be that the 50 millivolt VIA 0050 with 50 millivolts input range and the VIA 0250 differ only in the input voltage range, but would give the same output voltage range. So depending on the shunt we want to connect, we would choose the device to match the input voltage range of the shunt. To show the customer how to design these current sensing application based on the VIA parts and based on our shunts, we have two reference designs. One showing a current sense solution based on the VIA 0050 together with a WSLP SMD shunt, and the other one would be a solution based again on the VIA 005 DD isolation amplifier, but compared with a bus bar shunt to sense much higher currents than in the SMD version. Both designs can be accessed via the Vishay website. Design files such as Gerber files or Altium projects can be used to derive own projects.
So, Simon, what about the isolated voltage sensing using the VIA isolation amplifier?
For isolation voltage sensing, we have actually two possibilities. One would be to use the dedicated part, the VIA 200 SD, which is built for voltage sensing. This one can be connected directly to a high voltage voltage divider, dividing the input voltage down to a input range the IC can handle, and then output it to an ADC or whatever. This is limited to durational voltages since the input can not go negative. If we want to measure negative voltages, such as in an AC application, we can use the VIA 0250 with the differential input to counter the leakage currents from the device. We would add the R-sense resistor as seen in the graphics, and then therefore create a AC input capable solution outputting the voltage sensing signal to an ADC again. And this approach we have demonstrated in reference designs as well. So again, on the website you can find two designs, one intended to show how isolated voltage sensing with the VIA 20200 can work. This one uses a chip divider to sense voltages up to 1000 volts and divides this down to the 2-volt input range of the VIA 2000 and then outputs the signal onto the pin header. And the other one is intended to do voltage measurements of AC signals such as grid line voltages. It uses normal resistive dividers and uses the VIA 2050DD SD isolation amplifier.
So, Simon, does Vishay offer any other reference designs for isolated current and voltage sensing?
Vishay puts quite an emphasis on creating reference designs for all the products, and so we released a series of reference designs in 2025 and before that. Here we have listed the new additions from 2025, including the 4 reference designs we've just shown before. And in addition to that, we, for example, have high voltage intelligent battery sensor, which can measure high currents and output data via a CAN bus. We have some active discharge reference designs, and then we have also some newer eFuse power stages. In addition to that, you will find much more designs on the website, and new additions are coming on a quarterly basis. Our reference designs you can find on vishay.com under the Resources and Reference tab, or you can enter www.vishay.com reference-designs.
Fantastic. Well, Simon, I think that's all I have time for today. Thank you so much for joining me.
Thank you for having me.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Vishay. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.